Hey there, STEM Chemistry. This is Miss Ruark. This is Vodcast 9.2, where we're going to talk about pH, pOH, how they're related to acids and bases. Okay, so properties of acids and bases. We need to get into talking about the differences between the two. Okay, so acids. Let me make sure I've got a color that's going to work. I think this one will work. Okay, so acids actually have a sour taste to them. Okay, think citric, that was cute. Citrus fruits, okay? Oranges are sour a little bit, right? Lemons are sour, limes are sour, okay? Those are all acids. Okay, they're going to give us a sharp stinging pain when they're put into a cut. That's not a good thing. They react with metals. Okay, they are called proton donors because they give away a hydrogen ion. Why do we call this a proton? Well, let's think about it. Hydrogen has one proton and one electron, right? Well, if we don't have the electron there, what are we left with? We're just left with a proton. So a hydrogen ion is called a proton. Right? They have a high concentration of hydrogen ions, and they range from 0 to 6.9 on the pH scale. Okay, 0 would be the strongest acids, and 6.9 would be the weakest acids. All right, so enough about acids. Let's move on to bases. Oh yeah, and I got to play you guys great songs. I'll play it in class. I'm not going to sing it right now. I'm not going to torture y'all. Okay, taste. So acids will taste sour. Bases will taste bitter. Okay, bitter. They feel very slippery. Okay, think about soap. When you get soap on your hands and your hands kind of slip, or if you ever get bleach on your hands, that slippery feeling, that is a base. Okay, they can dissolve organic matter, and organic matter is anything that's carbon-based. Okay, we've done some work with some carbon-based substances before in the class, so that would be considered an organic matter. Okay, these are called proton acceptors, and that's because they can always take a proton or a hydrogen ion. They have a high concentration of hydroxide ions, and on the pH scale they range from 7.1 to 14. Okay, the strongest base on this will be 14, and the weakest base would be at a 7.1. Pretty simple, right? Okay, well here is a pH range of its acid-base indicators. Okay, and we use these acid-base indicators to give a visual of the pH of a solution based on its color. So depending on which pH or which indicator you use, let's say that we were to use phenolphthalein, the colorless color here means that it's an acid, and when it turns pink, it's a base. And in between, where it's just faintly a color, it just means that it is kind of at its equivalence point. Okay, if you had thymol blue, it actually has two changes. So it goes from red to yellow, and then from yellow to blue. Okay, so when it's acidic, it's red, yellow would be its neutral, and then blue would be its basic. Okay, so all of these have different color changes depending on the range that they are showing. All right, acid-base reactions. If you mix an acid with a base, it's going to either form water or it's going to neutralize the other one. Right? So it's going to form water or it's going to neutralize, and that's why we call these neutralization reactions. Because an acid with a base, oops, I guess I can write that down here, right? An acid, HCl, with a base, let's say we have NaOH, is always going to produce a salt and water. So what happens is the hydrogen ion from your acid combines with the hydroxide ion from your base, and they're going to form water, or they're going to neutralize each other. That makes sense, right? All right, to neutralize something, when something is at a pH of 7, which is what water's at, we say it's neutral. Okay, that means that it's going to have the same amount of H's or OH's as it does H pluses. It's neutral. All right. I can't talk right now. Acid-base calculations. So what does that mean? Well, that just means that you're determining what the concentration of hydrogen ions and hydroxide ions is. So in a neutral solution, the molar concentrations of hydrogen ions and hydroxide ions are going to be equal. They are equal to each other. Right? In water, hydroxide ions, the molar concentration of hydroxide ions, that's what that means. Molar concentration of hydroxide ions, so we put that in there, hydroxide ions, okay, is equal to the molar concentration of hydroxide ions, and it is equal to a concentration of 1.0 times 10 to the negative 7th. Okay. Now, in water, we know that H plus and OH minus come together to form water, and we know that water can break apart into H plus and OH minus, and that's what we call the auto-ionization of water, is where it can go from water molecular water to ions, and from ions to molecular water. All right. For other solutions, though, if we have an increase in the hydrogen ion concentration, then guess what? The hydroxide ion concentration is going to decrease, and vice versa, which means that if we have a decrease in the hydrogen ion concentration, then the hydroxide ion concentration will increase. It's a direct or indirect relationship. One goes up, the other goes down, right? Seesaw. Okay. So how do we use the pH scale? Well, pH is just kind of simply saying power of hydrogen, right? Because we're just talking about how many hydrogens we have. So if we have a pH equal to 7, we say that the solution is neutral, and our hydrogen ion concentration is equal to 1 times 10 to the negative 7th. That was pretty easy, right? Okay, so pH is just telling us, well, we'll get there. All right, if we have a pH that's less than 7, we have an acidic solution, and that means that our hydrogen ion concentration is greater than 1 times 10 to the negative 7th. And then if we have a pH that's greater than 7, it's a basic solution, and our hydrogen ion concentration is less than 1 times 10 to the negative 7th. All right, so how do we calculate pH? Well, pH is a negative log of the concentration of hydroxide ions. Now, the nice thing about this is that this negative cancels out with the negative on the exponent, right? And all we're going to end up being saying here is that the log of this concentration is, well, what's your exponent? Essentially, that's what it's saying, right? Okay, so the pOH is the power of hydroxide. So all we're going to do is we're going to look for the negative log of the hydroxide ion concentration. So if I'm asking for pH, make sure that you have hydrogen ion concentration. If I ask for pOH, make sure you have hydroxide ion concentration. Okay, oh, go back. Now the nice thing about pH and pOH is that they both equal up to 14. So if you add pH with pOH, they equal to 14. Okay, there's something else that you need to write down. Write this down. Kw is the water constant, and that tells us that the constant for water is going to be 1.0 times 10 to the negative 14th. So our hydroxide ion concentration and our hydrogen ion concentration should always give us a product, of 1.0 times 10 to the negative 14th. So we can multiply one times the other, and we should get this number here. That number is going to come back to help us later, okay? Not in this podcast, but soon. All right, so how do we calculate pH if the hydrogen ion concentration is 1 times 10 to the negative 7th molars? All right, well, pH is equal to the negative log of the hydrogen ion concentration. So we put in negative log of 1 times 10 to the negative 7th. Okay. Let me plug this into our calculator. Now, it depends on the type of calculator you have. If you plug this into your calculator, depending on what you have, you could either hit negative log and then whatever. Okay, there are other ones that you have to punch that in and then do log negative. It just depends on the calculator that you have. Now, you should end up with a pH of 7. That's what you should end up with. Okay, so double check and make sure that you get that. If you're not getting that and you can't figure it out, punching it in a bunch of different ways, bring me your calculator so I can help you figure it out, okay? All right. Okay, so complete the following chart. Now, I'll go through this pretty quickly with, ooh, I didn't mean to do that. Ooh, I didn't mean to do that either. Let's try, oh, there we go. Okay, let's go through this quickly. So if we have a 10 to the negative 4th, that means our pH is going to be 4, right? If I have a 10 to the negative 10 of OH, that means my pOH will be a 10. If the pH is small, it's acidic. All right, so, and the way I got the 4 and the 10 is I said, well, remember pH plus pOH is equal to, why is my pen acting so funny, is equal to 14. So I just take this and plug it in and solve for the one I'm missing. All right, so if I have a pH of 9, that means that my hydroxide ion concentration should be 1 times 10 to the negative 9 molarity. If 9 is my pH, then my pOH would have to be 5, right? 14 minus 9. And that means that my hydroxide ion concentration would be 1 times 10 to the negative 5th. That's easy, right? Okay, if my OH concentration is 1 times 10 to the negative 5th, then my pOH is 5. That means my pH is 9, which means that this is 1 times 10 to the negative 9th. Pretty easy, right? Both of these have a pH of 9, which is greater than 7, so they are both basic. All right. 10 to the negative 1 tells me that my pH is a 1. That means that this is an acid. It is a strong acid. Okay, if this is 1, then this one has to be 13 because remember it's out of 14 total. So this would be 1 times 10 to the negative 13th. All right, that was a hot mess. All right, good. Okay, last one here says, what if it's an incomplete dissociation? Then what if it's a weak acid and it doesn't completely break apart? All right, well, what does that mean? Well, that means here we have, what is the pH of something that only breaks apart 8% of the time? And the solution is a 0.100 molar solution. All right, well, that means that out of this, 0.8 of it's going to break apart. So how do we figure out what that total is? Well, we take this and we multiply it by the concentration. All right, and when we multiply that, it gives us 0.008 molar of this solution will be hydrogen ion concentrations. The rest of it is not dissociated, so it's still clumped up together. Okay, and then to figure out our pH, we take the pH, which is the negative log of hydroxide ion or hydrogen ion concentration. So we plug that in and we put it into our calculator. You should get 2.0969100013 blah 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 blah. All right, we need 3 significant figures. So 2.10 is my pH. That wasn't so bad, right? And I think that's it. It is. So I guess I'll see you in class.